Well, good afternoon, everyone. Welcome to the last session of the afternoon. My name is Matt Haubrick. I'm with the Iowa Department of Transportation. I'll be your moderator for this session. I want to thank you for coming in to our performance management track for our session on innovative uses of visualization in operations and planning. So looking forward to some great presentations. I do have a quick note on the program. The second presentation listed in the program, automating data for operations, decision-making, and performance measures from Utah Department of Transportation. That speaker has not been able to make it today, so we're going to only have two presentations in this particular session. Because of that change, we will be doing a little bit of Q&A after each one of the other two speakers, and then we'll do a little panel at the end. So we'll try to make the best use of the time that we have available, and if we run short on time, maybe we can do some trivia or something like that. I don't know, so we'll figure it out. But anyway, thank you so much for being here. Hopefully a few more folks will trickle in, but it's we got the big room for this, so it's nice to kind of be comfy and sit out in the audience. I'm going to go ahead and actually just sort of mention the speakers and let them kind of introduce themselves so that we can kind of make the best use of everyone's time here this afternoon. So to start out with, I'm going to just introduce Charles Lattimer, who is with the University of Maryland Cat Lab, and he'll be our first presenter, talking about visualizing traffic signal performance. So Charles, take it away.
Thank you, Matt. So yes, I am from the Cat Lab, University of Maryland Cat Lab, and we are talking about traffic signal performance. And there we go. All right, so let's kind of start off here talking about, let's see, there we go. So today's presentation, so I'm going to give a brief introduction to traffic signal performance and kind of how we can use visualization to understand how traffic signals and arterials are working, and ways that we can use those for to make better decisions on how to operate them and improve things. So we'll talk a little bit about kind of the two flavors, I'm going to say, of traffic signal performance measures, ATSPM versus trajectory-based measures. Kind of get into some examples of some visualizations, some little case studies of how we've used visualizations to improve traffic signals, and we'll have some time for questions at the end, as Matt was mentioning. So, traffic signal performance measures. That's kind of we've seen a lot over the years with performance measures on highways. Those are a lot easier to model and and look at, because you have like a continuous flow and those kinds of things, and finding incidents. Traffic signals a little tougher because you have basic networks. I mean, you have stops. The traffic is stopping, and it's a much you have a grid system. It's a bit easier, a little bit harder to kind of zero in on those kinds of things. We've seen agencies recently, I'd say probably over the past 5 to 10 years, kind of moving to an idea of using data from their traffic controller systems, in order to make decisions. So the idea, instead of being reactive, kind of moving to a proactive management of their traffic signals. And that leads to more efficient signal operations, and it also provides data for those agencies to communicate to their stakeholders, to communicate outcomes. We spent all this money to fix this road, and this is the improvement that we've seen. So it's this is the example of the traditional traffic signal timing process. So it starts very linear. So it starts with a trigger. So it could be a complaint. A lot of traffic signals are retimed on a 3 to 5 year process. So there's some kind of a start trigger. Bring the designers in, we'll hire a consultant, let's do turning movement counts, let's collect data, let's stick them into the synchro model, model all the scenarios, figure out what the traffic signal timing should be. We'll go ahead and implement those. We'll send those out, put those into the controller, send some people out in the field, do some floating car runs, fine-tune those, come up with a nice report, hand that over to the client, and then we're done, right? We can just kind of sit around and wait for another 5 years and hope nothing happens, right? That's kind of that's the old way of doing it, Performance-based signal timing is a cyclical process. So you start off, basically the concept is you monitor the signals all the time with data coming in from the traffic controllers or from trajectory-based vehicles. We'll see that in a minute, kind of the other way. But data is coming in all the time. It's being examined by a system. Either the system can identify issues, or it submits reports that maybe somebody gets an email every day that kind of has like the top 5 issues, or they can something that an operator can look at to say, okay, something doesn't seem right here. The data suggests solutions to the problem, and then the technicians can go out and deploy a fix. And this is something that can happen, in a period of hours or minutes, when it's done right. And then you repeat. So the fix is deployed, you monitor the signals. Did it fix something? Yes, it did. Perfect. And if not, you kind of wait and kind of check every day or a process to see when the next problem happens. When this is done well, you can find problems before the public does, which is, so to be able to fix something before a complaint comes in is always, that's always time savings and really always a win for the agency. So 2 main flavors, I'm going to say, of traffic signal performance measurement. So the one that people mostly talk about is something called ATSPM, and automated traffic signal performance measures. That's something that Utah DOT, we're going to hear from Utah here in a little bit, but they were pioneers in that, along with Purdue. And the idea, I call that like a bottom-up approach. So it's based upon high-resolution detector data that is then analyzed, and then you derive the traffic performance from that, from that data at the bottom. Another way is a top-down approach, and that's kind of what we're doing at University of Maryland, is we start with the vehicle data. How is the traffic moving? And then we boil that down to say, okay, how does that affect the intersection? So it's kind of moving in a different direction. And we'll see an example of that in a second. So first off, ATSPM. So the way that works is you have your traffic signal controller is collecting high-resolution data. So you can imagine traffic controller is basically a computer that sits in the traffic signal cabinet, and in this case it's every time you have all these channels with all these different detectors on there, every time something happens, like a phase changes, signal changes, head button's pushed, a car rolls over a detector, there's an input into that controller. And there's a log file that like 10 times a second will record everything that happens on that controller. That information is then sent to some kind of a central computer, that has the ATSPM software on it. It'll keep track of that, and then it'll build some visualizations that the engineers can look at and say, okay, this is what's happening kind of in the past here on the intersection. You don't have to have detection, but it really, in theory, but that really adds a lot of value to, what you're able to do and what kind of graphics you're able to, visualization you're able to build from that. So those are kind of the main 5 pieces. And this is an example of, one of many outputs that you can get from an ATSPM system. This is the Purdue coordination diagram. And it's a pretty busy diagram, and it's something you kind of have to be a little bit of a traffic engineer to understand everything, but I'm going to kind of try to boil it down a little bit to simplify it a bit here. So each one of these, there we go. All right. So at the top here, you can see these are the different signal timing plans. So the concept is that for different times of the day, you have a different signal timing plan that gives a different emphasis to different movements of traffic. And so that's kind of what these colored bands are coming down. And so I'm going to zoom in on one of those. So this is like a middle of the day plan. So what we're seeing here on this graph is at the bottom, we have, this is the time of day. So 10 o'clock, 11 o'clock, 12 o'clock. Each one of these dots is a vehicle that is passing over a detector. And this is the cycle time. So you can imagine you're sitting at it kind of runs on red, yellow, green, and then you wait there and you have red, yellow, green. So there's a cycle that kind of goes around for that. So this is like one particular movement. So this is like the northbound through traffic. So down at the bottom, this is when we call the cycle time start. So the kind of basically goes red here. people sitting at the traffic. So this is traffic coming in on red. This is when here's our time here, so 90 seconds. This is when the green starts. So 90 seconds to about 120 or so, 150 this is the green time, and there's your yellow, and it turns red. So cycle begins, turns green, turns red, ends, and then comes back down here to the bottom again. So cars arriving on red are all these little dots here. Cars arriving on green are these dots here. This is bad, and this is good, right? So let's take a look at that. Using that knowledge, let's take a look at this diagram. So this is before the signal is optimized. Look at all these cars arriving on red, and not very many arriving on green. So after they re-optimize the signal, so you can come up to the signal beforehand, change the timing, release the cars a little bit different time, and now they're arriving on green. So you can very easily see, the dots move from there up to there. So that's kind of a good feedback that that this particular change in signal timing was good. So now let's look at the other approach there, which is we're going to call the kind of the top-down approach, the one based on the probe data. So this is based. You may have heard of a lot of data from INRIX and HERE, TomTom, things that are used for highway performance measures. So this is a very different data set. This one is based on trajectory data, so it's pulling in data from the vehicles on like a 3 to 5 second ping rate, so it's very fast. And because of that, in the background, they're able to see where the vehicles go, but also as they approach an intersection, you can see them slow down and determine what movements they make at an intersection. So if we were to basically take an intersection and draw a box around it, so we have like an inbound segment, so here's our stop line. So I believe it's like 150 meters ahead of the intersection and about 80 meters out is kind of what we're defining as the intersection. So we can see when a car comes in, if this is the approach speed, so we have over time on the bottom, so hits this, travels up through, we're going to have a pretty continuous line here, so it's going to be pretty steady slope, so no stop. So that's going to be our reference speed moving through the intersection. If the vehicle stops, you'll see it'll slow down, which is kind of what this red is, and then it'll start back up again once the signal changes. So this difference between kind of our reference travel time and the observed is that's going to be our delay. So we can directly measure the delay of the vehicles passing through the intersection, kind of using this type of methodology. So I'm going to switch over here to a tool that we are working on, that we've developed here. So this is what we call the traffic signal analytics tool that the Cat Lab's working on. This has been deployed in several states. I believe we're looking at Florida right now, so this is kind of the Orlando area. But basically, what you can do with the tool here is you can pick different intersections. So I'm going to using this map-based thing here. So you can kind of grab, say, a box. I want to take a look at this collection of intersections, add that to the list. I can then pick what time period I want to analyze. So these are the date ranges. So I can go back today is the 3rd. So I can go back to yesterday to get data, or or go back in time. So pick up to a month worth of data. Then select the different days of the week I want to look at. So maybe the weekends, maybe just Thursdays, maybe just weekdays. And then pick the time of the day, either 24 hours, or I can maybe pick the morning rush hour, PM, midday. And then submit the report. And once that comes back, this is kind of an example of what we get. So for each intersection, we get what we call like an intersection breakdown diagram here. So just lost my... There you go. All right. So at the top here is a table. I'm going to expand this out a little bit because my screen's a little small. So this is a table of all the different intersection movements that are shown that are part of my data set. So from there, I can then sort through and then pick which movements I want to take a look at. If I want to look at just through movements, I can sort those out of the table there and scrunch that down, or just left turn movements. I can also rank them by number of split failures, level of service, different travel times, and approach delay through the intersections, so I'm able to do that. On the map down here, and this is kind of where the visualization is kind of neat, is this is what we call the intersection breakdown diagram. And you can see in this particular diagram, we can change the colors so this is percent on green. So the way that the diagram is drawn is we have the different colors that are associated with the values, and also the length of the arrow. So you can see the ones with the low percent on green values have the short arrows, the ones that have the higher percent on green have the longer values, longer arrows. The thickness of the arrow is also dependent upon the volume of traffic that we see. So looking at this intersection, we can see this north-south. This is going to be the predominant movement through the intersection. We have kind of a thick through arrow, and then the ones on the side are a little bit thinner. And also we have the traffic north and south has a higher percent on green than the cross traffic, which is what you'd expect, particularly for rush hour. So you're timing your signal to be able to accommodate that through traffic on the major movement north and south. As we click on these, we can see it'll also update the map on the side to be able to correlate, so you can see on the map what your movement is. So here's like a southbound through movement. Here's my northbound through movement, and kind of east and westbound. If we hover over that, we can see what the observed vehicle count was. And again, these are sampled vehicles. This is not like if you were to stand out there by the side of the road with a clicker, you'd get a higher number than this. But this is the ones that have been picked up with the probe data coming through the system. Let's see what else we got here. Okay, so we talked about that. All right, so let's take a look at a couple use cases where this has been used before. So how are the signals in my county performing? This is a question that a traffic engineer might ask. So we're going to take a look at using the ranked intersection table and talking about weekday split failures. So real quick, a split failure, for those of you who haven't taken traffic engineering recently, you've all experienced these. So let's say you come up to you're sitting at a red light, and there's a line of traffic in front of you. Light turns green, you roll forward, but then the light turns red before you get to the intersection, and you got to stop again. So you just experienced a split failure, a cycle failure. So the idea is you're supposed to take you at least only one red light to get through, and when you don't, you have a split failure. So this is an example from Washington County, Oregon, some of the traffic engineers out there. So what they did was they decided, I'm going to take a look, they're going to look at the kind of the top 10. If you go back to the previous slide there's that table at the top where you can rank your movements. So they said, okay, what are my top 10 worst movements where I've got the most split failures, in a month? So they went through and they ranked them. So, okay, June, here we are. This is number 1, number 2, number 3, number 4, down to number 10. In May, the previous month, they did the same thing. And then they kind of looked over here and they said, okay, well, this one I know was bad because it was like in the previous 5 months, it was in the top 10 every month, so that gets a score of 100%. This one was only in the top 10 once, so that's 1 out of 5, 20%. They looked down this list and they said, yep, that's about what we'd expect to see. That one, we know that one's the intersection's bad, the intersection's bad. But this one, we don't know anything that's going on out there that would cause that to be in the top 10 every month. I mean, there's nothing happening there, so what's going on? So then they went out and they took a look, they pulled up the data, and sure enough, this one particular movement, there were 39 split failures on this one left turn movement on the intersection, and pretty much nothing else on the other ones. So there's a lot more on this one, but is there a way that what happens if I gave that one movement a little bit more time to kind of extended that time for just a few more seconds for that left turn arrows to see what happens? And so they did. They decided I think they added like 5 more seconds to the arrow, and they did it before and after. And you can see the movement went down from 39 split failures down to 3, kind of in the same comparable time period, and without really adding many more to the other movements. So this is kind of one example of kind of finding the problem and kind of suggesting a solution in order to fix it. So here's a second case study that we did a little more recently. So that was looking at kind of over a time range, but what if I wanted to zero in on a specific time of day and see how things are changing like within that time period? So this is something that we did for Fort Bragg recently. I'm going to just kind of show you a couple examples of how we plotted this data, and this just kind of give you some inspiration on ways that you can do this too. So here, this is one particular intersection, and so they had a morning event every morning that they had a lot of traffic coming in for, and you can see that as it piles up, you know, coming up to the so at about 6:30 is when that happened. So you can see that the traffic volume really peaks here right before, and we're starting to get, I have it coded where the red are number of split failures, and you can see that here. The percent on green is this blue line, drops way down. And then if we kind of take a look at that a little bit different way, here's this yellow line, this orange is the traffic volume again. You know, it mirrors what we see here in this, in the bar graphs. What I'm also plotting here, in the box plots, is the control delay and the approach speed. So if we look at this particular left movement, we can see that we have our baseline, kind of our control delay, you know, about 20 to 60 seconds is kind of what you normally see, and it creeps way up here during this time of high traffic volume. So that's definitely kind of quantifying that problem that they were seeing. We also see the approach speed go way down here. It goes down, but it also gets narrower. So if you can imagine, if you have a queued line of traffic, you're kind of limited how fast you can speed back up to. And so that's kind of what you're seeing here. So so you can't get all the way back up to speed before you have to stop again. So that tells me that there's a queue spilling back here that's outside that detection zone. So if we take a look at the other direction, kind of the competing direction, we don't see that. So this is our through traffic on this movement. The control delay is pretty flat. There's not quite as much traffic volume, and the approach speed is about the same too. So that tells me there may be some excess capacity here that we could probably steal some of this through time and give to the green and see if that could particularly solve the problem. Kind of a final thing that we're working on right now, this is a tool we have under development. I mean, this should be out hopefully by the end of the year, is an intersection matrix tool. So this is let's kind of step that up and kind of zoom out a bit. You know, if we could take like an entire week's worth of data and put it onto a single matrix and then kind of look at that by day of the week, say, Monday through Sunday, and then time of day, we can then zero in and say, okay, these are the specific times of the day that we then need to go back and do more detailed analysis on in order to find out what the problems are. So, and this is going to be set up per movement, so you'll be able to click through these, and then these charts will change on that. So we're pretty excited about this. Hopefully it'll be out by TRB annual meeting. If not, it'll be out just shortly after that. So. Well, so in conclusion, just want to just hopefully I've inspired you, given you some good examples of how we can visualize traffic signal data, and maybe giving you inspiration on how to do things better and differently. And yeah, it's a wide open field right now, and we're really excited to see what else comes. So thank you. All right, thank you, Charles. Any questions for Charles? Move on. Yeah. Yes, sir.
How does that all change with the oncoming of connected vehicles and so on? Does that make your job of keeping track of the traffic volume better?
Well, so all of this is this is connected vehicle data. I mean, in a sense, this is not data like, well, there's a couple different flavors of connected vehicle. There's the coming in from the roadside versus this is like what we call like a third-party connected vehicle data type of thing. But conceivably, you could use that the roadside data could be fed into a system very similar to that, and so the more data, the better, really, because as I would say. But.
Yeah.
Yeah.
In these sections, have you factored in pedestrian or cyclists and their impact on the traffic?
Saying pedestrian, not at this point. That's not in this data set, but that's something certainly we would like to do. You know, that's now ATSPM. They do in that set, since it's pulling stuff right out of the controller. It does pick up, you know, ped button pushes, and you know, so you can, you know, more easily take a look at the pedestrian in that. Through this, you'd have to have some other data sources. I mean, we would love to be able to kind of marry both of these things together, you know, and be able to kind of and get it all in one spot. But we're not quite there yet, but we think that's coming. So,
Great. Thank you.
Yes.
So is this automated? Are these happening automated, or is there a person who's looking at this data and saying, "I agree, change the signal type"?
This is all data coming in. So this is not tied into the system. This is not making changes to the system. This would be reports coming to an operator, coming to an engineer to say, hello, we've got a problem here. Here's your daily email. This traffic signal blew up. You know, you might want to go take a look at it. So it's, yeah. Any other questions? Or?
Great discussion.
All right.
Thanks very much.
Thank you, Matt.
All right, and for those of you that maybe came in a little bit after we started, just a quick program note. Rikki Sonnen from UDOT, I don't believe is with us today. Rikki, unless you're in the audience, raise your hand, speak now. We'll scrub that presentation off of the agenda this afternoon, gives us a little bit more time to hear from our other speakers. So our third speaker here is Bill Hereth, who is with the Wasatch Regional Front, and he's going to talk to us a little bit about visualizing transportation planning data, through an interactive web app. So come on up, Bill.
Thank you. Let me just get plugged in here. First of all, sad to miss Rikki. I've seen Rikki present, and she does a great job. And also, this is probably the most intimidating place I've presented in. And I'm told when I'm nervous, I speak really fast. So either that's good or bad. I can get through this really quick, or you won't understand anything I'm saying. So we'll try to keep it nice and good pace. So first of all, I'm Bill Hereth. I'm from the Wasatch Front Regional Council. I'm a professional engineer. I've only been with Wasatch Front for 2 years. Prior to that, I was in the private industry as a traffic engineer, transportation planner. Got my undergraduate degree in civil engineering from Brigham Young University in Utah, and then went to Ohio State University for graduate school. I got a dual degree there in city and regional planning and civil engineering. So I've always felt the pull between planning and engineering, and hopefully some of these apps will kind of show that. So first off, my goal is to spend most of the time showing live demos. I hope they work. I do have a backup video just in case things go south, but I just want to spend most of my time showing 6 different apps that I've made at Wasatch Front Regional Council. So first, to introduce us, we are an MPO in Utah. We comprise 4 counties and 60 local communities. And as you know, the West is growing pretty quickly. Utah is ranked the fastest growing state since the last census, and by 2050, it'll reach about 5 million people. So there in blue is our area, and then Mountain Land Association of Governments is an MPO just south of us. And we share land use and travel demand models. So these applications work for both areas, and so that's about 75% of the state of Utah. So just before I get into the demos, kind of the philosophy behind these, we have a wide range of data. As everyone knows, there's tons of data out there. We have, as MPO, we have lots of forecasts. We have all of our model outputs from our travel demand model. We have our land use model outputs. Our land use model uses parcel-based data And it's estimated every year between the base year 2019 and the horizon year 2050. So we get lots of data from those sources. We also have big data. We've acquired streetlight data together with UDOT and other agencies in the state. We use that. So we're trying to take all this data and present it in a way to our diverse audience. We have elected officials, we have professionals that work for cities and states and agencies, and also the public. With all the growth, there's a lot of public demand for information. So some of these tools are good for dealing with public audiences. And we want it to be a way, because this diverse audience, they aren't engineers, we want it to be easy and seamless. So we want it to be able to invite exploration. So someone can open the app, go to their space that they're familiar with, kind of get an idea how things look and work, and then kind of explore around the area and kind of get an idea of other areas just to orient themselves. And we also provide lots of supporting information in the apps. And I've seen that providing the information this way does help foster a solutions mindset. So I don't know if I'm not familiar with other places in the US, but Utah's growing so fast, we seem to have a victim mindset. This growth is happening to us. Let's stop it. This is kind of the initial reaction. But through some of these tools, we hope to change that to a solutions mindset where people see the problems, see the issues, but also see information that can form new ideas, think of new things that maybe we aren't thinking of, or that they see it from a different point of view. It can help inform the process. And one example of that, I used to serve on our local city planning commission, and we're always complaining about the city just west of us has lots of vacant land that's growing really fast, and all the traffic goes through our community. So that's something we harp on a lot. After showing some of the OD tools to the commission, it seemed to open up a new way of thinking about it. Like, oh wow, look at this issue. It's not just us, it's happening across the region, and what can we do to make it better, to just plan for all this? So this is called the lightning round. I want to demo 6 interactive web apps. It's a lightning round because you'll probably think I'm going too fast and you want me to slow down or something, but I just want to show the breadth of visualizations we have, information we have, show you the breadth, and hopefully if you want more information, you can go back to this presentation. There's a link to a demo I recorded, or you can visit some of these individually. So I'm going to start with the Utah statewide ADT forecast map. So first of all, this is a statewide data set, unlike the other apps. So we, in partnership with UDOT, with the other 5 MPOs in the state of Utah, we've combined all of our forecasts for each year of our regional transportation plans into one place. So let's just zoom into the Salt Lake City area. So the legend here on the side, the lowest are the blue and the highest the red. We're trying to simplify things. If you want to know the numbers, you can click on this and see the ranges. But you can step through the different plan years, and the map will automatically update to show you the information. So here in Lehigh, we're growing in Lehigh, growing pretty fast, but out here in Eagle Mountain, there's all this vacant land that's growing pretty fast too. So you see by 2050, by 2050 we have a new freeway going out there, we have other roads. If you want to see the change from year to year, you can click the ADT change. So from 2019 to 2050, you can see the high growth in this area. You can see the only arterial here. If you can see my mouse, I don't know if, I think so, hopefully. And this blue line, this is Redwood Road. It's a parallel arterial to this new freeway. So as volumes grow on this new freeway that's built, then the Redwood Road drops. So you can see the increase in volume. If you can read that, it's 147,000 on this freeway, ADT, and it drops 13 to 20,000 on the arterial. So any community can go in and see how their roadway projects are affecting their traffic. and you can step through the various years. So you can go through the plan. This is to the first phase, or to the STIP projects. You can see new freeways and the drops in arterials. Here, Bangor Highway, which is an expressway with signalized intersections every mile or so, it gets converted into a grade-separated freeway, so you can see the drop in parallel corridors, the volumes there. So it's just a quick way for someone to go in and orient themselves. Here's Sandy. They add a lot more freeway crossings between interchanges, so you can see the drop at the interchange and the increase on the new crossings. So, and if you need detail, let's say you live where I live here by this road here, you can click on it and it'll give you a chart showing the historical volumes. You can see this, I don't trust the UDOT counts there as much, but it's about 1,000 ADT. This now has connected to I-15. So now it's going all the way up to, it's projected to go up to 38,000 in 2024, and then drop again. And you can see why it's dropping. Here we have a new crossing of the Jordan River, and so the traffic is actually the same volume. It just kind of switches from one to the other road. Try to go faster here. I'm going too slow. The advanced version, you can get population employment forecasts to help understand the roadway change or the volume changes. So you can go to any TAS in the whole state, zoom in. You can see the numbers. This is the number of population. You can get total employment, retail, industrial, office. You can do all that. You can see the change. So here, the growth from 2019 to 2050. You can see the change in density. So here, in Salt Lake County, you can see where it densifies along I-15. If you want to say, hey, let's look at just a sub area, you can click on some of these TASs. Let's turn off auto zoom. I get dizzy if that's on. Okay. So you can click on the TASs, and as you click, you can see the employment projections for this selection of TASs, and it will automatically update. You can get more information from there, and if you want to do an entire city or county, you can do that. So Iron County in southern Utah. So that's the projection, population employment forecast. You can also get the plan projects, so you can hopefully understand what's happening over the life of the plan. You can select a phase or a mode. So phase one, the first phase of the plan, you can toggle between roads and transit or add both. So it's a quick way for city staff, public officials, anyone to go in, get oriented. If you're dealing with someone who has a question, calls your city, you can perhaps show this to them, share some information with them, and it's all in a single place to do that. Our next app is the Access to Opportunities app. So I don't know if it's just us that calls it Access to Opportunities, but this is pretty much destination accessibility. So how accessible are different destinations to you? So here are jobs, how accessible. Here's a sentence completion task or interface. So show me the auto access to jobs within a typical commute compared to the average for the entire Wasatch Front. So this is a heat map. The red colors are the highest number of jobs that are accessible to you for that TAS, and then the blue is the cold, or lowest number of jobs. So you can see west of Lehigh, this high growth area is currently there are very few jobs accessible within a typical commute. If you change that to transit, you can see the big impact to transit. Let's say you're in a small community up here in Ogden, and you don't want to see, compared to the region, because you're so low, maybe you can go to northern Weber County, and you can see, okay, within our region, what's the range of accessibility. So you can do regional level comparisons. Let's see, and then there's also If you click on a TAS, I keep picking on my home TAS, maybe I'm more comfortable there, I don't know. You can see it has a chart with the TAS's accessibility to jobs by auto compared to the region. So the TAS in purple and the region in gray. So you can kind of get a feel for that. And as you toggle between things, that changes and adapts automatically. You can also turn on the travel shed display. So maybe go to auto. So here, from my TAS, how far can I get in 10, 20, and 30 30-minute increments? So I can see how that compares in 2019 to the future, how it changes. If it goes fast enough, maybe you can see it, the difference. So you can get an idea with the projects, how does your travel change? And this is pretty reactive too, as you click through the Wasatch Front. It's pretty quick at updating, which is really nice. And then if you want to see, let's turn that off. You can also see the future projection. So between now and the future, you can see the net gain, where it gains the most. So have no fear, Eagle Mountain, in 2050, you will have a much greater access to jobs. So you can see this area grows quite a bit. And that's where a lot of the growth is projected for this region. Okay, our next app is the traffic congestion forecast. So I don't know, as a traffic engineer, this is really just a map of, sorry, I have a link here. This is V over C ratios from the travel demand model. We do adjust the volumes to match the forecast, or we adjust based on the forecast, so it's not pure model output, but it's adjusted. And you can have, you can see the V over C ratios for any scenario. So not just the financially constrained, those are the scenarios in the RTP, but you can also see like the no-build scenario. So I'm from Lehigh, I can go there and see, oh, that's awful in 2050. And okay, that's not too bad. You still have this pinch point because of our geography. We have a pinch point here, we call it point of the mountain. But you can also see the travel demand model only has the model period V over C's for 3 hour. We have 3 hour peak AM, 3 hour peak PM. But we can factor these based on the continuous count station data from UDOT. So we can go down to the peak hour. So basically based on your facility type and your mostly facility type, what's the factor for that conversion? So you can hopefully get a more refined view of travel conditions and not just the bigger 3 hour window. And then if I know the UDOT Region 2 director has told me he's lost himself for hours in this map. So if you want to really see lots of fun data, you can click on any segment. It'll put the V over C's in the sidebar here, side by side. That one looks bad no matter what. So maybe don't live over there. But here by my house, you can see no build, it's high, it's red, but in the build it's green, low, or yellow. And then you can see these are the forecasts. These should be the same as the other map for the scenario shown there. You can see the segment capacities, the lanes. And if you really want to geek out, you can get all the factors. So the traffic engineers, when they first saw this, like, okay, well, like, how did you get that V over C? And they're like, okay, I need to show you the day of week factor, the period factor, the direction factor, the truck factor. So this has all of that ready for them to look at your numbers and see if they make sense. And it's divided by functional group. If you're on a freeway, we have HOV lanes separate. If you have frontage roads, we have the arterial separate. So here, we have 3 different facilities on this one segment, and we display all the V over C's for each of those, but the map will only display the worst V over C for any combination. Okay, and our next app will be, hopefully it doesn't feel like I'm going fast enough, but I think we have time. Residential destination accessibility. So let me close some of this. So this was developed in conjunction with Weber County. We developed a residential accessibility app. This was to help communities try to locate housing in areas where there are accessible destinations that residents would like. So maybe the best way to see this app is let's go to Payson. They were our rivals when I was growing up in Spanish Fork. But here on the side, I just cleared the results. So initially it'll load with the default set of priorities for each measure. So a city or staff can go in and click on their community, see the different measures here. If you click on show, it'll show you the data behind this. So there's the daycare centers and there's the transit lines. So a community can set their own priorities. They have a high priority on childcare, then the map adjusts to show the highest. It's based on buffers around the childcare locations. If you add another measure, transit set the same priority. This is where they overlap, is the highest blues. And then we have city centers. Part of our visioning plan through the region is to define which areas are centers. So where you want to concentrate growth. And so those are predefined. So you can see the orange outline here. If we prioritize that with high priority, then the combination of the three, that will show up as the highest in this heat map. And if you want to understand, like, oh, why my house is right here, why does it score so low? You can click on any location, and a sidebar will open with the scoring, with each measure, the score that it scored for that at that location, and then the weight of the priority that you gave it. And so here, if I live here, I get 33% of the possible for the city, for this community. So that's a good way to quickly allow communities to kind of go in, set their own priorities, and see how things pan out. And if you're going crazy, you want to go through multiple communities, you keep clicking, and you can see based on all these communities where the heat map shows the highest scoring locations. I think that's that one. Okay, and then we have, with our streetlight data, if you know, like big data, it's big and it's hard to see, so we tried to make this easier for others to see. Origin distance, so we call this our trip movement estimates. We have a little disclaimer because what the data means. But here it starts out, this is an origin destination map with kind of like a heat map, but the colors are kind of the rainbow colors, I guess. And this shows, turn off labels. So we have small districts defined throughout the region. So we have someone from Cottonwood Heights saying, oh, we should put an express bus from us to the university, and how many people travel there? So that's a question, we get that question quite a bit. Cottonwood, we've gotten that same question multiple times. So you can click on here, you can see the sidebar, you can see there's 83,000 trips in 2019. So this average daily, 83,000, and above those at the university, we have 360 going to the university itself, and then several hundred around it. So you can see how many ride are all vehicles. You can also do, if you go to the advanced version, we like to hide the advanced version, hide stuff in the advanced version because it's a little harder to interpret maybe. Or the data is not as nice as we like it. So you can see how many people ride the bus from Cottonwood Heights up to, did I turn off the labels? Yes. Cottonwood Heights up to the university. So only a handful, 11 people are riding up to the university. And these volumes are adjusted by streetlight, so they tell us it is more representative, so it's not just the sample, but the disclaimers kind of explain that. And we only have data for some modes 4 months of the year, and it only goes through 2020, not through 2021 yet. As you click on a region, you can get, or a district, You can get a breakdown of different charts, so you can see by mode, by month, by time of day. So you can get the data kind of parsed out at different levels. And this quickly adjusts, so if you're in Lehigh, you're just exploring, you see, oh, how do I compare to Provo? And you can go just down to Provo and see quickly like the difference between the two. So it's a tool meant to designed to help with answer questions, multiple questions, or even spur ideas or questions that people didn't know they had until they started looking at this. So let's see. So there's that one, and then I think this is our last one, and then I will kind of go through some of the nuts and bolts of this. I guess I've gone faster than I thought, so maybe get into some more details about how I built these. Okay, so we're going to go to the Household and Job Forecast Viewer. So we are currently in the process of updating our regional transportation plan with a base year 2019, but the plan will be through 2023 to 2050. So this is the new forecasts that are being prepared for that plan. So these have not been adopted, so they're still up for comment and for change through our land use model and our process. But one thing cool about this is you can change the geography of your forecast. So if you're a city, you want to see TAS by TAS, you can go in here, turn on your labels and see how the households spread throughout your community. You can see also density, count or density. If you want to see how you compare with other cities, not at the TAS level, at the city level, you can click to city area. So you can see how Lehigh and Eagle Mountain, Lehigh is 34,000, Eagle Mountain in 2050 has a projection of 58,000. So how that changes. If you go to the base year 2019, you can see currently they only have 10,000. So you can click on this, see the change. So this will give you that quick calculation, or that number in your head. Lehigh grows by 13,000 households over the 2019 to 2050, and Eagle Mountain by 48,000. If you want to step through every 5 years, you can go in 5-year increments. The first 5 years, Lehigh grows by 3,300, Eagle Mountain 46. You can go through time, traveling through time, into the future, your own time machine. Lehigh is kind of plateauing at around 1,000. Eagle Mountain's still growing strong at 83,000. If you click on Eagle Mountain, you want to understand that better. You can see the trends. Let's turn some of these off. Let's look at just the population trend. So you can see it's still growing pretty quick. It's not really tapering off anytime soon. Lehigh is kind of flattening out over time. In yellow, there's the chart with all the numbers. If you want to see, so in yellow, it'll highlight what numbers are being shown, or the difference. Those are the two numbers that you take the difference. So as you go through it, the yellows will change, so you can kind of follow along if you're kind of getting lost in this sea of data. You can have office, retail. We have a combined factor, household job intensity. So we try to weight the two jobs and households and provide a single number. So that's there too. And then, sorry, there's a lot here. There's percent changes, there's densities. So Lehigh grows by 5.2% that time. Let's go to the advanced version. The advanced version, if you want to see, I like seeing as a percent of the county, how much is your growth. So if you click on here, household job, no, let's go to households. Okay, okay, absolute change. Some of these numbers, I don't know what they mean since it's haven't explored exactly, but here, household count as a percent of the total county growth. Let's go to the plan, from plan to plan. So from 2019 to 2050, Lehigh experiences 6% of the total county growth is in Lehigh. Eagle Mountain has 22% of the entire county growth. So that's quite a bit of the county. If you want to go to region, you can see at a region level. The entire Wasatch Front, Lehigh's growth is 2.2% of the entire region. Eagle Mountain has 8% of the entire growth. So You can understand why Lehi's a little scared of Eagle Mountain, because it's just, there's so much land out there that it has a high growth potential. You can also look at new versus old. We never like to compare one plan to the other because we don't like things changing on people. Oh, we said this last year, but this year it's different. Let's turn off percent of growth. So you can see, in 2050, Lehi is projected to be 5,700 fewer households than we projected last time. So it's a drop in our projection. Eagle Mountain's 13,000 more, so it just keeps getting more and more. And here on the side chart, you can put them side by side if you want. Let's do Eagle Mountain, more interesting. Population, maybe better scale. I need to adjust it so the scale is dynamic. But you can see the difference between the forecasts. The new forecasts that we're preparing are the dark line, and the old forecast is the light line. So just easy to do that. You can do that for any set of categories. So that's the demos. I will just have a couple slides, kind of the nuts and bolts. This was built using ArcGIS Web App Builder. I downloaded the SDK to my desktop and developed on my desktop. I created a custom widget. That's kind of a blank widget, kind of a shell that you can put with your own information. I created the maps on ArcGIS Online, and then I used JavaScript and HTML to build the widgets. So I didn't know JavaScript before I started these apps, so it's been about a few years, so I had to learn a new language, which was fun. And then used Dojo. So this is the 3.x API. There's a new version, the 4 point something. So that's probably where I'll head next, to kind of leave this environment and go to a new environment. But I didn't really feel comfortable as I'm not really a web developer, so I didn't feel as comfortable just starting on my own without anything. So the web app builder was a nice kind of training wheels for me. So, and all the data, a lot of the data is pre-processed in Jupyter Notebook using Python. Yeah, I think we went through a lot of this. And here I just wanted to show kind of, this is one of the final slides. There's a lot of data in here. So for instance, if you look at the household and job forecast map, the last one we looked at, any combination, there's 53,550 possible map displays. So depending on which button you click, you can get one of any of those 53,550, which is, I think, is kind of crazy. But yeah, just imagine what we would do. We'd print static maps, PDFs, and kind of email them to people. So imagine printing a 53,550 map PDF of each possible combination, emailing it out. Here you go. So this is a much easier way for people to feel comfortable, orient themselves, answer questions, diverse amount of questions. And then the feature classes, this is how much data is in the feature class on ArcGIS Online. So I'm really going from 2 megabytes at the lowest to like 425 megabytes. The residential destination accessibility was built off parcel data, so it was the one we didn't think would work that well, but there's not too much. The performance is surprising given the amount of data that's in there. And then the JSON, for some reason I'm using JSON a lot. I don't remember, but that's just a text file. It's a way to format a text file and access it. It's public data, so I'm not worried about keeping it behind in a secure database. So the trip movement estimates, that's 4 gigabytes of data behind that one app. And it's only 2 megabytes. So all the calculations are done in JavaScript and then updated instantly onto the map. So here's my contact. If you have any questions, please feel free to email me. I'm happy to share information. We do have GitHub repositories with some of these. I need to brush up on my GitHub skills because I'm a little slow at getting those updated. We have additional interactive web apps. Here's 6 right here. A lot of the TDM ones I'd like to use for internal use to understand how the TDM works, but these are all publicly available. And then there's our maps gallery with more maps than we have. So that's it.